Okay, so it's probably going to be a kind of brief lecture today. In many ways, I think in the future I probably won't do tests on Tuesday. It's resulting in a kind of weird week. What we're looking at numerical estimation of integrals. And topic of the day is the trapezoidal rule. And the trapezoidal rule is really important. It's the rule that gets used a lot in real world applications where a function is expressed in terms of a table. So the idea behind the trapezoidal rule is easy to state. You've got a function from A to B. You want to estimate the area of this function. Well, the traditional way of doing that, the way that results in Riemann sums and integrals, is that we cut this region into pieces and we create rectangles and we find the area of the rectangles and we add them all up. And I mean, if we ask why rectangles, well, because they kind of do a good job of approximating the area. I mean, imagine if instead of using rectangles, we try to use triangles. That's clearly no good. So they do a pretty good job of representing the area, and we can find the area of a rectangle. And that second part's important because the whole point of this process is to replace something that we can't do, finding the area under a curve, with something that we can do, finding the area of rectangles. Well, there's another shape we could use. I've sort of given the game away by putting the name of the rule on the board that would work better. I mean, in terms of like developing the integral, it wouldn't work better because it's more complicated. We use rectangles for Riemann sums because they're the simplest shape that works. But as far as you know, approximating the area under the curve on this interval, what if instead of using rectangles, we used trapezoids? Well, you can see that the area of that trapezoid and the area under the curve are really close to each other. I mean, just looking at this visually, this is clearly doing a better job than a rectangle, where you've got all of this stuff and you've got all of that stuff, and that's all error. So using a trapezoid makes sense. Oops. Well, assuming that we can find the area of a trapezoid. I'm sure that at some point in some high school class, you've seen the area of a trapezoid, but seeing something 5 years ago in high school and having it at the tip of your fingers are a little different. Fortunately, the area of a trapezoid is pretty intuitive. So we have two different heights, and we have a width. The area of a rectangle is the width times the height. Well, we can't quite do that here, but we do something very similar. We average the heights and then take that average and multiply it by the width. So we can find these areas, and the trapezoidal rule comes from using trapezoids and from using this area formula instead of the rectangular base times the height formula. And in theory, you can always do this, but the trapezoidal rule works really, really well when all the intervals are the same length. So we can always use the trapezoidal rule. And the trapezoidal rule requires us to take this interval and cut it into little pieces. And there's nothing that inherently requires the pieces we cut that interval in to be of the same length. There's no law that says we can't do this. I mean, we can draw the trapezoids. But we really, really want to not be in this situation. We really, really want them to all have the same width. And I keep talking about tables. And fortunately, this is something that's usually true when you have tables of data. Like if you take a measurement every month, then the width of all of the intervals is going to be 1 month. If you are in a hospital and you're taking measurements every hour, the width of all of the intervals is going to be 1 hour. So this is something that's realistic to expect. And let's see what happens when we use this idea. Let's draw a function and let's find the area under the curve. Let's break this into this might become a little tedious, but let's break this into 8 intervals. And we'll call, we traditionally talk about going from A to B. We'll call A x sub 0, and then we'll have x sub 1, 2, 3, 4, 5, 6, 7. So B is x sub 8. And in the formula, we're going to need to know the length of one of those little intervals, and exactly the same as for the midpoint rule. Delta x is going to be b minus a divided by n, where n is the number of intervals. And I'm going to make this easier to write. So here is x sub 0, and here's x sub 1. The trapezoidal rule says, well, create a trapezoid that looks like this and find its area. And this is f of x sub 0, and this is f of x sub 1. But if you're using the trapezoidal rule, or this is true for the midpoint rule as well, if you're using any of these rules with a large number of intervals, this becomes kind of clunky. I mean, just writing the f of notation, and whatever, however many times, 10, I think. So we replace it. This height at x1 we call y1. This height at x0 we call y0. And then similarly, this height at x2 we call y2. And with this, I'll stop, but this height at x3 we call y3, and so on. So let's find the areas of those first three trapezoids, and let's see if a pattern emerges. So the area of the first of these is the average of the heights. So y0 plus y1 all divided by 2 times delta x. And I'm going to go ahead and make the observation that we can rewrite this. Here, 2 is a constant, delta x is a constant. This is delta x over 2 times y0 plus y1. And what about this second trapezoid? What's y1 plus y2 all divided by 2 times delta x. So delta x over 2 times y1 plus y2. And the third one is y2 plus y3 over 2 delta x. Delta x over 2 y2 plus y3. And let's ask what happens if we put these together. And this is not going to be, because we're only looking at 3 of these trapezoids, this is not going to be the entire integral. It's going to be this area here. But it's probably enough for us to sort of see the pattern that's going to emerge. Here's the first term. Y1 plus y2 y2 plus y3. So we see this, we want to simplify it. What's the first thing that's crying out at us here?
To multiply by 2.
We could multiply by 2. But multiplying by 2 requires us to have an equation. So we can multiply both sides of it by 2. So if this is approximating the integral, multiplying it by 2 would give us a formula for double the integral. So that's a good thought, but it's probably not quite where we want to go.
You could factor out the delta x's over 2.
We can factor out the delta x's over 2. And as far as simplifying this, what comes next?
Combine like terms.
Combine like terms. We have multiple y1s, we have multiple y2s. We do not have multiple y0s. And we do not have multiple y3s. So you see that the two middle terms have a 2 in front of them, but the first and the last term do not. Now, if we were to take this sum and we were to keep going, we'd get the delta x over 2 y3 plus y4. So if we took this and we expanded it, so we include a new trapezoid, you see what happens, we get another y3. So now these y3s combine together. And now it's the y4 that's by itself. And this pattern, keeps going if we add in the next trapezoid. This will give us another y4, so we'll have a 2 in front of the y4, but it will also give us a y5 with nothing in front of it. So the trapezoidal rule becomes the integral from a to b of f of x dx is approximately delta x over 2, where this delta x depends on how many rectangles we're using. It's b minus a over n. So delta x over 2 times y0 plus 2y1 plus 2y2. And all of these terms have 2's in front of them, except for the first term and the last term. And there's the trapezoidal rule. And the trapezoidal rule has a few things about it that I really like. I mean, the midpoint rule, it's clumsy in the sense that it requires you to write down a lot of information that you don't actually use when you use the midpoint rule, right? Because you've got a function and you've got an interval, and the first thing you have to do is take that interval and cut it into pieces. But then those pieces aren't what you actually need, so you have to find the midpoints. The trapezoidal rule doesn't have anything like that. When you're using the trapezoidal rule, these pieces are what you're using to create the trapezoid. So it's very direct with no extra sort of busy work that you have to do. Another advantage of the trapezoidal rule, and I've mentioned this before, but it works really well when you have tables. As long as the data that you're looking at is being collected reliably and regularly, like every hour or every 15 minutes or something like that. And that's because, you know, when you have a table, you're being given part of a graph, essentially. You're being given a very small part of a graph. But if suppose you have the following table, X, Y, 0, 1, 2, 3, 4, 0, 5, 3, 1, 2. Just kind of making something up. And this Y will use function notation. And we say, okay, this is all we have, but we need the integral. How can we find the integral? Well, what we've got, let's see, let me change the scale a little. We'll just draw this on the Cartesian plane. 1, 2, 3, 4, 5. 1, 2, 3, 4. We've got the point 0, 0, 1, 5, 2, 3, 3, 1, 4, 2. And that's all we know. And we want to try to approximate the area under the curve. Well, this data, I mean, it might not seem like we know a lot, but we know exactly enough to hit this with the trapezoidal rule. Because the trapezoidal rule would say, well, you cut your interval into pieces, and then you create a bunch of trapezoids like that. We couldn't use the midpoint rule here, because to use the midpoint rule, we need to know, for example, what the function is at this point, and we do not have that data. So the trapezoidal rule is exactly what we need for tables. And I mean, the trapezoidal rule, I keep saying we like our data to be equally spaced. That's true, but I mean, it's not literally mandatory, the trapezoidal rule will continue to work if the next data point I have is this. But the downside of that is that we'll no longer have this nice formula. This formula requires that the intervals all be of the same length. So we now have to approach this a little more manually. We would have to find the areas of each of these trapezoids and add them together without the formula. Or maybe what's more likely is that we would use the formula to find the area up to here and then just find this area separately and add it on. So sort of a classic example of this from the field of medicine is the area under a drug concentration time curve. So a drug is administered to a patient, and the concentration of the drug in this patient's bloodstream is monitored. Let's say a nurse goes in and checks it every hour, or there's a computer system set up that does this automatically, but you get the following data. So what you don't have, but what you clearly might be interested in, is the total contact with the drug. Because I mean, maybe the drug is potentially dangerous. I mean, you see this a lot in cancer, right? You have radioactive tracers in the patient's bloodstream, and you do not want the patient to be exposed to a bunch of radiation. So the question you'd ask is less, what's the concentration of this radioactive substance at a specific time, and more, what's the total amount of this radioactive substance that the patient is being exposed to. And that's given by the integral. And this is maybe not totally obvious, but you know, think of it in terms of graphs. If the concentration graph looks like that, the patient is not being exposed to a lot of the drug. If the concentration graph looks like that, the patient is being exposed to more of the drug. How do you measure the difference between this and this? Well, in terms of calculus, This example, where the patient is only being exposed a little, has a very small area under the curve. Whereas in this example here, the patient has a very large area under the curve. So we need an integral. And we don't have an equation. I mean, we don't have anything that we can hit with the fundamental theorem of calculus. But we do have this table of data, and this is all that we need to use the trapezoidal rule. So we look at the table and we verify that these measurements are regular and that they occur at units of 1. Every time t goes up by 1, I guess I'd better say delta t then. Every time t goes up by 1, we get a new measurement. And there we go. So there's a little formula for this delta, but when you're looking at graphs, you just read it off. And we should have that delta divided by 2. And now we just read these y values right off the graph, remembering that all of the y values except for the first one and the last one need to be doubled. So 100 plus 2 times 71 plus 2 times 50 plus 2 times 35 plus 25. The first and the last two aren't doubled, the rest of them are. And now we just go to, I would ordinarily say our calculator, but I'm still fighting to make it acknowledge this license, so we can go to Wolfram Alpha, and I know that people watching this video aren't seeing anything. I'll share a screen in just a tick. See, we type it into, this is essentially a calculator website, and we press enter. And here we go, 218.5. The 218.5 watt. The units are a little weird here. And let's see, I don't have them in my notes, but we can figure it out. I mean, this 100 and this 71 and this so forth are all milligrams per liter. This one is a time, this one is 1 hour. So milligrams per liter times hours is the concentration unit, or I should say the contact unit. And that's the trapezoidal rule. And there's one rule left. Again, if I really wanted to, I could just do it today, I suppose, but it would be kind of rushed, and then what would we do tomorrow? So we'll adjourn slightly early today and talk about Simpson's rule tomorrow.